All right, everyone. We are going to be looking at the Monty Hall. I guess I can't do not Monty Python, but Monty Hall game show problem. So let's go ahead and start getting everything ready. Let's see. All right, so what is the premise of the Monty Hall problem? Let's see. It's a little dark outside. It's a little... there's an old inside joke here. All right. Let's see. I feel like I'm sitting very low today. I don't know if my chair is rising. Nothing seems to be matching up today. Hope everyone is doing well. Let me get my microphone here close to my face. There we go. So what is the premise of the Monty Hall? So it's a probability. Probability? Yeah, it's not statistics. It's a probability. So there's a car, and there's a goat, and there's a goat. And what we have to do is we're going to be proving if we switch doors. So the premise is a contestant, big old bobblehead over here. Oh, that's awesome. All right. So the contestant picks a door. They don't know the contestant. They don't know where the car is. They want to get the car, of course. Now the host, Monty Hall, he's over here. He's standing. He's with the audience. He has a little microphone. Oh, that looks kind of cool. He's got a little microphone. And so the contestant picks a door. Now, the host comes over here. And he opens this door. And he says, "Hey, do you want to switch?" And the guest goes, this isn't the contestant. We already have a C here. The contestant goes, "Okay." They think it's a 50-50 chance between these two because there's two doors left, and they go, "Okay, this is 50-50. So I'm just gonna," and here's the thing about human nature. The person typically stays. Well, what the host and the people of the show, somebody somewhere did the math. If when they stay, they only have a 33% chance of winning. But when they switch, that is not an S. When they switch, they have a 66% chance of winning. So the show, it changes by a factor of 2. And the host and the producers of the show understood this about human nature, that typically everybody stayed. So they were able to have a awesome game show. People watched it all the time, and most people stuck with their guess. So they won. This is some pretty good odds. The host won 60% of the time. So now we need to design an algorithm to test this, to find out if this is actually right. So let's get started. Now, I haven't done this in a very long time, so we'll go ahead and get started. Now, I do not want to do what I've done the past in the past week, where I begin to over-engineer this. So we're gonna do baby steps with this, because I got this to work last time, and then we're also gonna do some edge case testing and some validation, and just go from there. So let's go ahead and get started. All right. So if you were here yesterday, we worked So we're going to need to be working with a list. So we have three numbers, 3 indexes, 3 choices. All right, so doors. Let's just go ahead and make this real simple. It's going to be a car, a goat, and a goat. Then we need to bring in from random import shuffle. Now, why would we be needing to bring in shuffle? Because we're going to randomly. So if you think about it, we randomly shuffle and then we randomly pick. So we're just going to reshuffle these. Well, actually, now that I think about it, we'll randomly shuffle this and then we'll randomly pick an index. Yeah, how about we do that? And let's remind ourselves how shuffle works, just in case you are new here today. And if you are new, thanks for joining us. Let's do dir on shuffle. And nope, we're doing help on shuffle. Okay, because I need to remind myself, and this is what's important. You want to remember and understand the important things. You don't want to try to, hey, Unfinished, how are you doing today? Hope you're doing well. We are looking at the Monty Hall game show, and we're going to prove that switching your doors after seeing where one of the goats is, that it is a greater chance of winning the car after you make a switch. So we need to handle a lot of randomness. So we of course brought in. Actually, now that I think about this, no, we'll do rand int and random shuffle. So, all right. So I brought in doors and then shuffle. All right. So I have shuffle and I pass in a list and it does it in place. So when I get shuffle, pass in doors. You do know the game. Okay, so do you understand? Because this took me, as the math part of it, I still am suspicious of the math, but I get it, because you now have 2 of the doors, and when we swap, it's 2 out of 3, which is 66%. So we are going to be doing this to test this, because I remember I got a lot of hate when I put this video up originally on YouTube, and I read the actual history of when the math got challenged, and I did some research, and people in the math community lost their stuff over it. It was very interesting. It was a big deal. I think it was in the 70s. But yeah, so we're going to be writing an algorithm to prove that switching is best. So now let's go ahead and also, do you know shuffle, I think, because we did that yesterday. Do you know rand int? So okay. You should think like a number. Door is 1,000. You choose 1, and the other 98 are open. Yes, you're 100%. I have seen that illustration, and that did actually help, because you're like, okay, yeah, because you think when you take things to an extreme, it's easier to comprehend. So 100% agree with that. Random, and then dir random. And we're going to do rand int. So if you do not know rand int, it is a very helpful tool. So random dot, let's do help random dot rand int. And if you look at it, rand int, oops, break it up into pieces, random integer. That's the way I remember when I first read it. All right. Now, here's a little change in what we're not used to. So I get a random integer range A and B, including both ends. So this is the only example where it is not exclusive. So if I told you pick a number between 0 and 2 are our two endpoints, you could possibly get 0 and 2. So we need to bring this in from random import rand int. You can also do this way. Let me show you. So that works. And you can also do comma rand int, just like that. But I can't remember if that is frowned upon. So all right, let's run this. Let's get everything into memory. So we have rand int. We need, so we're going to shuffle this. Shuffle doors. And then now I'm going to choose a random index. So choice equals rand int and 0 to 2, because I'm having to convert this to an index. So now what we're going to do is we're literally going to use, and we used pop yesterday. So we have doors and dir on. Did that really shuffle? Are you kidding me? Is it not really? It's run twice and not shuffled anything? There we go. Okay. I'm like, am I misspelling something? But it wasn't throwing any flags. All right. So I finally got the car to move. Just wanted to double check and make sure I was typing everything. So, all right. So now my choice picked index 0. So what are we doing here? All right, we got some people dropping in. So hello, everybody. Don't know exactly where you are, but it's morning for me. It's probably evening for most of you jumping in. We're going to be writing an algorithm to prove the Monty Hall probability, that if you change your first guess to your second guess after you see a goat behind a door, you double your probability of winning the car. So what we've designed so far is we've brought in shuffle and we've brought in rand int. So we've moved the door, we've created our doors, we've shuffled them randomly. You're randomly making your decision, and then now we're about to pick it right here. So we're going to need to use pop, because list dot or dir on list, and we're going to utilize pop because we want to take this out of the list. And so we're going to be going through here, picking one, making our guess, removing that from the list, and then the other one, the host will come in and show us a door. And then basically, so if we think about it, we're going to remove one of them, because right now our choice was, I believe, 0. So we would be removing the car, we'd be taking this out of the list, and we're going to utilize pop. So it moves that item from the index. So we need to pass in. So let me show you how list dot pop works if you did not join us yesterday. So this is a very useful method in Python for a Python list. It removes it and returns. Removes and returns. So you can use pop to get it out of the list, and if you want to keep it, you don't have to do any other magic to it. It automatically. So if I were to come here and do guess, because I took doors, not fours, dot pop, and then I passed in my choice, I would literally be let's print guess. So check this out. So when I do this right here, I get goat, and now doors is down to 2 objects. So now, all right, so let's go through these steps. So the steps are easy. Keeping up with the probability of what if you won or not, that's going to be the more challenging from what I remember. So we make a guess. So right now there's only one path right now because we need to test if they won. So up until a point, it's one main path, and then we're going to diverge between switching and not switching. So right now, we've made a decision, and then we're about to be shown one of the other doors. All right. So right now, so here's our guess, and here's our doors. So right now, the contestant is not winning. So what needs to happen now is the host needs to remove the other goat. All right, so let's think about this with our Python brain. So I need to remove a G from our list. All right, so we can do this a couple of ways. So let's look at it. So we got dir on list. Is it literally going to be? All right, so help on list dot remove. All right. Remove the first occurrence. So we could have a discussion of we could argue that with this example, we could get nitty-gritty into the statistics. Python now is going to be looking constantly at our first, like if this example, if let's say the contestant picked the car, it would always remove the 0 index, the very first door. So it would always show door number 1. Now, we could argue that isn't probability, blah, 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 blah. But in our example, we're just going to be proving that switching is right. Does that make sense? So we're not going to be, it won't affect the probability of the switch, but in this example, the host would always be opening the first door. So we're going to be okay with that. So we're going to use the remove function. So now we need to go doors dot remove, and we're going to pass in. So what do we pass in? Remove first occurrence of value. So value, so it's literally what is it? So it is a G. So now we're going to print the guess and the doors so we can begin to see what this looks like. All right, let's run this again. again, again. Okay, so see, this is no way. All right, so we need to make sure. But this is actually beginning to show our point. Is that how many times already did this happen? Now, the more we do this, the more it's going to show. But here's a first example, because I was just testing to make sure. But this is how this is. Is that we ran this 1, 2, 3, 4, 5, 6. 6 of them would have won out of. So this is the example. The car was remaining 6 out of the 7 times. So if they would have switched their guess. Hey Nico, how are you? Oh, give me a second. I think people are starting to stir. Maybe you need to go feed the dogs. All right, give me a couple minutes. I'll be back. Okay. My wife's actually going to feed them this morning. So she's like, did you mute it? I was like, no. I said, I think everybody likes getting to hear. So I don't know if you can hear the medium size one. Oh, the color is so bad. All right. So let's go ahead and get going. Nico, I like that. Don't leave. I appreciate it, Nico. All right. So this roughly, very quickly, proves our point that, and sadly, that's just one of them. So that's the mid-sized dog. We have a larger dog and then a smaller dog, and he the best we can figure it out is that he is cheering us on while we're making his food. All right, so here we go. So now we need to switch our guess. So we need to have a way to switch to test and then not switch. So let's just go ahead and get these paths going. We just need to make a decision and stick with it. Okay. He's almost done barking. Sorry, I don't know what was more annoying, having me be gone and hear the dogs barking, or having me talk and hear the dogs barking. Okay, so like I said, we need to now have a way to switch. So we don't really need to make any other determinations, because if we look, it's the only thing left. So let's revisit. So we make our first guess. The host is going to show us another door. There's only one choice left. There's just one choice left. So it would be new. Okay, sorry Nico. There was a game show. Unfinished is familiar with it. It's a game show that came out. It's called the Monty Hall. I call it the Monty Hall problem. Let's see. When was the game show on? I think it was on in the 60s. And I'm going to confirm when it was on. Game show, Monty Hall. When did the show run? Monty Hall show. Let's see. Can't find it, but I want to say Monty Hall problem, Monty Hall show. 1975. All right. So what the premise was that the contestant there were 3 doors. There was a car behind one of them and 2 goats behind each of the subsequent remaining doors. The contestant would make a choice. The host would show one of the other doors, the one with a goat. So then the contestant didn't know what was behind their door, but knew one door with a goat. So they had 2 doors left, one with a goat, one with a car. And the probability states that there is a 66% chance of them winning if they switch doors. And what the contestants typically did is they stayed. They stayed with their original choice. Because when a novice at math, they go, all right, I have 2 doors, I have a 50-50 chance. Mathematically, that is not accurate. Because now you've actually made a 66% chance because you're down a door out of the 3. So the premise of this is you need to switch, and you have a 66% chance of winning when you switch because you gained more knowledge. And there was actually a big deal discussed, and some mathematicians got into some very heated arguments about. Is the timer going? Okay. The live stream is acting weird again. So what we're doing is we're designing an algorithm to actually test, to prove the hypothesis that switching doors has a higher probability of you winning the car. And we just did this very quickly. Out of 7 examples, 6 of them you would have won the car if you would have switched. So we're doing Python brain. We're doing Python brain we're doing human brain to Python brain. So we're having to utilize the random module a lot. So we created a list of doors. We're shuffling them. We're randomly picking a number between, in Python, 1 and 3, 0, 1, and 2, and then we're making our choice. And then right here, this is where the host is showing. Host is showing a goat. And he would literally have a goat behind the door. I've seen old clips of this. And then you didn't know what was behind your door. So you had to make a decision. Should I switch? Because the first time I heard about this problem was my oldest son's math class is 7th or 8th grade math. And I was like, this would be a great Python problem. So the teacher let me come in, and I had done this all at home. It took me a while to figure this out. And we actually, because they did it in class longhand and proved that it was better to switch. Well, I wrote an algorithm where we could do this 10,000, a million times. And of course, the more you do a statistical problem, the more it approaches 66, 6, 6, 6, 6. Same thing with flipping a coin. So if we were to write a program, an algorithm to sit here and flip a coin randomly to pick the with those 2 choices randomly, it would approach, you would be off a little bit, but it would approach 50% the more you did it. So, all right. So really quickly, 6 out of 7 right here, it proved So the more we would do this, the more it would approach 66%. But right now it's overarching that switching our guess is the way it needs to be done. So here we go. Let's see. So now we need to switch. So literally our second guess is not an empty list. It's a list with one item in it. So literally this is all it's going to be. So it's doors index 0. Does that make sense? So we won't need to print out doors. Can you make a program that calculates how much force and what angle I would need to throw a bottle to land correctly? Oh, you're talking about the flip challenge? I think Python actually has a physics module. But how much? So you said to calculate the force. Yeah, I mean, you would have to. It would probably be easy to write the formula, but to actually have it and to know what angle to throw, because you're talking about very, very specific angles and specific force, and to actually then be able to. The only thing I've ever seen to be able to track that is on Mythbusters, where they actually had a angle where they actually would measure the degrees of angle of how to throw something, the approach angle or the exit velocity angle. That was one of the examples that I saw them do. But yeah, technically you'd be able to do that. All right, let's get going and finish this. So we don't need to show the doors because it's going to be empty. So we're just going to second guess. Let's run this again. So here's 2 back to back. Run it again. Run it again. See, now already. So we had 2, 3 back to back, and already here we are. So now we need to figure out. So we need to have one function with switch and one function, because we're going to be calling these over and over again. So we need to play the game. We need a function to play the game. Then we need a function to switch and a function to not switch. So let's go ahead and get started. So basically, here's the heavy lifting of the design. And we're going to need to count, and then we need to track if they won. So we need to figure out a way, because this second guess, are they going to stay? Are they not? And is this guess going to be a car, or is it going to be a goat? But this is the main. We've done a lot of the heavy load lifting here because we've mimicked. We have our overall arching design. We've shuffled it. We've made a random decision and we've picked our choice. And then the game show host has shown us the goat. And then here we go. So let's go ahead and really kind of wrap this up. So let's see. We've been on. How long have we been going? The problem with this is random can't actually generate random stuff. It's impossible to. Yeah. But for this example, I mean, it's picking a number between 1 and 3. So it's close enough for our, because actually I would argue with as small as this is, it would act exactly like a human, because this number is so small. The repeatability of a human making choices, this would actually be more accurately associated with how a person would pick. But I do understand what you're saying is that, yes, technically there is no, it's called pseudo-random. So Nico is actually approaching a problem in computer science, is that there is actually no way to teach a computer to do a random choice. But then you study sociology, and human doesn't make random choices either. There are things that influence their decisions, and there's repeatability in those as well. So, all right. But very good point. It's technically not random. It's pseudo-random. It's as close to random as possible. But so is a human guess. So I would argue it's exactly like a human. All right, so let's go through this. We need to design a game. Def game. What do we want the game to do? Oh, that's not what I wanted it to do. So we need to do this. Do we want to be able to enter how many times we do it? Okay, so we're going to take in, let's take in times. How many times do we want to play this? How do we do that? So for game, attempts, rounds, time in times. Let's do that. There we go. So how I'm gonna design this is how many times to play the game. All right, this is what we're gonna do. Okay. So I'm gonna iterate through this. So right now, this would be if I switched. Why is the letter G showing a goat? Oh, okay. On 21. Gotcha. Great question. So let's go ahead and go through this. So, I think Nico jumped in here. So let's go back up here to this example, because I'm removing, this is when the host, this is mimicking when the host would show us a goat behind one of the doors. So you make your decision. You picked door 3. And the host comes up and goes, okay, I'm going to show you which door has a goat behind it. So we're just coming in here and we're using the tools that we have to show a goat. So I'm removing a goat from the list. So then what will be remaining, so the contestant made a choice, picked door 3. Then let's do this. Let's do an example. Whoa. Door. 1. 2. Don't know why this is so challenging. Okay. So here's Nico, great question. Let me go back over here so you can see. So contestant picked door 3. They pick goat. The host shows behind door 2, which is another goat. So that's what we're doing here. We're removing it from the list. So contestant made that choice. This is now removed. So these 2 are removed from our list. So the only thing left is door 1 or the car. So that's why now inside this list, we're picking index 0. So our second guess, it's going to be the only thing left in the list, because contestant picks 1, the host shows us one of the other doors, So we're down to just one door left that has not been picked yet. So that's what we're doing here on line 21. Does that make sense, Nico? All right. Great question. So we need to create two functions, one for switch and one for not switch. Def switch. There we go. I think that's right. So now it's basically this. Does that make sense? Bring this all in here. I don't know why when it's not in a function I want it like this, but when it's in a function I want it all piled on top of each other. I really don't know why. But when it's out in a script, I want spaces in between. Is that really weird? I feel like that's really weird, but my daughter would be like going, yes, because I know it's really weird. All right. Okay. Let's go back. Let's see. And then return second guess. Let's see. Guess is assigned but never used. Okay. So now we need to do def no switch. Switch. Yeah. All right. I'm trying to remake my old website. Here's another example. Made in Python that uses Flask. Oh, yes. I know I played around with I don't know if I did any videos on Flask, but I did some videos on Django a while back, trying to figure out if I really wanted to get into any web development, and it was very interesting to me, but I did not pursue and do anything with it. How easy is Flask to work with? Wow, that was bad. But how is it nice to work with? Django was a little complicated, but I didn't really finish with it. All right, so here we go. So no switch. We really don't need this because it doesn't matter. And this is guess. So, but we still need to keep this because we need to actually, to be clean, we don't really care about this. Because technically, I could just do pop and not have to assign it. But we know this works, so we're not going to change it. You use a decorator that turns a function into a path, and then you use return to decorators. Yes, decorators are very, very cool. I did. Thank you very much, Nico. So Nico's helped me realize that Discord is able to notice when you go live and it mutes. So it is connected. It is connected pretty deep in your operating system. So what it took a while to do was the notifications on Discord mute, and there is a banner at the top that says, all right, Nico just sent something. Yes. Oh, that is a perfect use of it. That is very good. I like that. That's very clean. That's really good, Nico. All right, let's get back. Let's get back to where we are. So we have a couple people dropping in. So kind of rehash here. We're going to design an algorithm to test the Monty Hall problem to prove that switching doors doubles your likelihood of winning. It goes from a 33% chance to a 66% chance, which is mind-boggling to me, but I finally wrapped my head around it. And if you look back in chat, Unfinished gave the perfect example that if you expand it and you take it to an extreme and you have 1,000 doors to choose from, and then I open up 998 of them, then that's some pretty good stuff, Nico. And you open up 998 of them, you're like, yeah, I want that other door. So you can go and practice the math, but what we're doing right now is we're just going to prove it. And if you look closely, and I actually got some pretty good hate telling me that I designed it wrong, but you can see right here that it's so accurate that you have to do it more to get it to approach 66, because we did this, I think we've done this 11 times already, and it is overwhelmingly switching. What is remaining is the door. And you can go back and watch, and it's a very simple concept to test. So we have our switch and we have our non-switch. So we have our game. We're going to pass in how many times we're going to check this, play the game, and then we're going to go. So we have our switch and our not switch function. Two different simple algorithms right here. And we need to now test the output of these decisions, switching or not switching, and see how many times they win. So, all right. Our output, so I run this. So I don't need this now. So let's comment this out. Let's see. I have two special buttons on a mouse, and if one does Control Z. Oh, that's funny. That's funny. I need to have a hot button for Control Z to undo. I never really used the Control Z very much, and now I seem to use it a lot. I guess once I started, once I learned about it and how powerful it was and how far back, it tracks a lot. It must use a lot on the clipboard. All right, okay. So we need to track wins. So we need to come in here, and we need to have wins equals 0, losses equals 0. Let's see. Let's see. Yeah. Now, because we need to, this is going to return, and let's kind of visualize this. So if I do this, if switch equals car. Oops. Control Z. Then wins increment by 1. Else losses increment by 1. Everybody understand what I'm doing here? And let's pass in. Hang on. We need to, because to be real, we need to be able to take in how many times do you want to play. Switch, change. Yeah. Here we go. All right. So what we're gonna do is we're gonna pass in a doc string. So we're gonna share what we're thinking. All right, hang on, Nico. I think you just sent me something else. Let's see what you got. Oh yeah. Okay. I do. That's pretty good. That's some pretty good stuff, Nico. All right. Okay, so we need to enter number of games, and if you are switching doors, not fours. Doors. All right, let's go from there. Change, yes or no. And decision, choice, decision. What do we want to call this? Because we need to do this up here. If change equal to y, then what variable do we want to choice, change, decision equals switch, else decision equals no switch. Yeah. Here we go. I'm liking this. So we're going to try this. I know I'm breaking my own rules right now by doing this. Because I just wrote a whole bunch of lines of code and we haven't tested any of it. So we have a few more people dropping in. So hello, everybody. Hope everyone is doing well. What we're doing is we're designing an algorithm to test the Monty Hall problem of switching doors and if we win. Let's just get the output. So print wins, losses. Game 10 times yes, not times. All right, let's run this. And we have all sorts of errors. On line 54 for time in times. All right. Range. All right. So that was a complete fail because I was trying to pass in a container. All right. Okay. That seems highly improbable. So let's see. I need to check something. Never mind. It might get loud here in a minute because we got some folks coming home. So and all right, so the likelihood of this that it's 10 and O is wrong. So we need to start breaking this down. Our decision. So this is garbage right now. So we need to let's see. Let's unpack what I've got right here. Global global dis, or is it non-local? We're gonna try something. So I want to. Okay. So has anybody ever seen this before? What I'm doing? So what I did is I kicked this outside of. I'm moving this variable, and you're gonna do this sometimes, especially if you need to pass information from maybe one function to another, and you don't want a function. You don't want that function to be nested. So I wanted to be able to call this. So this first time I called it, it said, "Hey, I have no idea what you're talking about," because this decision was inside this function. It's like, hey, you put it in a function, dude. You can't just come in here and say, hey, I want to look at this variable inside this function. I had to literally explicitly say, hey, all right, I want to be able to see this. I want to be able to see this object outside of this function. So I throw a keyword global in front of it. And then it goes, all right, you actually know what you're talking about. So when you call this, I'll go ahead and tell you what it's assigned to. And so right now, I'm not seeing where this is. Okay. Anybody else see what is happening? Because I need to run this function every single time. So this is the flaw. So if you look right here, this happens, this function, this actually needs to happen down here. Because the reason why this is all or none is because this is calling once. So this literally needs to be inside here. Let's check this. Let's see if I'm right. All right. And it's a little garbage. Hang on one second. Is that you? How'd everything go? Okay, and did you tell Mom? Because I don't know if Mom saw the text about the lake. Oh, no. Did you tell her? No. Okay. Okay, because she may or may not have seen it. All right. What's that? I don't know about it. Really? Okay. My daughter says, hey, everybody. Okay, now she's like, oh, no. Oh, but I don't know if anybody noticed, but yeah, my wife was actually looking around for stuff, and she actually was on the live stream a few days ago. She dropped in. So that cracked me up. All right, now let's rerun this and see what happens. Now, this is more likely. So let's run this. Now, here we go. All right, so does everybody see what I did wrong with the last code? I was having these choices happen outside the for loop. So that decision was being made once, locking it in, and not changing. So I need this to change. I need this function to rerun every single time. So there's probably a cleaner way to do this, but it's still doing what we want. But right now, this is just not making any sense. So let's see, wins. Let's clean this up. Wins. Oh my word. Wins, then curly brackets. Losses. Curly brackets. All right, so now, and then close this out. That work? Run this again. Oh, can you do me a favor? Can you bring me my protein drink out of the? My daughter jumped into the room, and I was like, now I'm giving her an errand. Oh, how'd the game go?
We lost.
Oh no.
We were winning, but they were like a little bit like my score prediction was 38-0. It was actually like 2014 maybe, 1914.
Okay.
But yeah, because we were winning 13-14.
Okay.
Okay.
All right. Sorry about that, everybody. I was getting an update. My daughter was at. No, you're fine. No, you're fine. My daughter went to a high school football game. All right. So now we're actually seeing real information. So now we need to track. All right. Let's start getting this really closer to. Oh wow! Look at this. Here we go. So just like I said, the closer we get to, or the larger the numbers get, the closer we get to the probability. And see how this is slowly approaching and getting closer and closer and closer and closer. All right. So this is switching. So we need to differentiate. So right now, this is just numbers, but we need to turn this into a percent. Let's clean this up. Let's do one more. All right, so print f string. We need to take, so wins. Is that it? Let's get this to work. Wins divided by times. Let's rerun this. All right, so we're getting close. All right. Percent equals wins divided by times 100. You heading out? All right. Be safe. I'll see you later. Love you. All right. So now I need to come over here and then do percent, and curly brackets, percent. And do we want to do the percent sign right after that? Okay, I've got an error. Something's illegal. Oh, I forget to close. All right, let's rerun this. All right, so we could truncate this. This will actually be something good to do. So this will be great practice. So right now, so did we switch? Let's get some more stuff in here. Switching, so if change, we could do this switching and no switching. We could figure out how we want to make this look. All right. If change is equivalent to y, yeah, let's do this here. Oh, that's not right. And there's Control Z really fast. Switched. And else didn't. Control Z. Like we should track how many times. Now see, also didn't switch. If we haven't talked about this, this is why I like double quotations, is because then you don't have to worry about a single quotation marks and you can use an apostrophe. All right, and switched, and 90. So right now that's getting better, but I didn't do anything, so I got technically a false positive. But we need to work on shortening this. Now, let's do an N. Percentage, let's change this. Percentage, percent wins, percent, winning percent. Winning percent, do we like that? Winning percent. Let's try, do we like how that looks? Didn't switch, winning percent, 33, blah, 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 blah. Let's round. Let's not truncate. We're not going to do padding. We're just going to round this. Okay? Let's do that. How long have we been on? Nico, you still here? We've had, apparently, statistics is not everyone's favorite. So, I just absolutely love all this. All right. So, let's see. Yeah. Let's round this. I don't want to truncate it. I don't want to do padding right now. I don't feel like padding because I have to look all that up. So we're going to handle this here. If you haven't seen the round function, that's another great tool to have in your toolbox. So not dir. All right, cool, Nico. Awesome. Thank you for hanging out with me today. Round. So what does round do? Round. All right. So I'm going to take in a number, round a number to a given precision decimal digit. Int digits. So defaults to none. Round a value to an integer if n digits is omitted. All right. So here's important. So it will round to a complete integer if n digits is omitted or none. So basically, it's default to none. So return a value of the same type as the number of digits, may be negative. So I actually found a gap in my last 2 weeks of work in VB.NET that rounding rounding with VB.NET inside SQL, it had a defect. It had a bug. Because if you passed it in 1, it rounded the whole number. And then if you passed it in 2, it would round it 2 decimals. Really, really weird. And yes, we did validation on it to make sure that it wasn't a whole number. All right. So we're going to round right here. Round. So, and we need to put this in parentheses because I want this math done properly. And then I'm going to wrap this around. And then I want this to be rounded to 2 decimals. So it tells us right here that this rounds to 2 decimals. Aha! So what happens if, should we do this and we pass in just the number and it just shows games? Because right now, I guess it has. Do we like winning percent above or below? I don't know how I feel about that. I think I like... I don't know. I go back and forth. I think I like it. Let's look at both. Let's look at both. Wins and losses. So we take, you didn't switch. You win out of, oh, wait a minute. Games played. Print F games played and times. Is that what we called it? We called it times. All right. Yep. So didn't switch. We got games played. Now let's see how this looks. Didn't switch. Games played. 100,000 games played. Wins 33,525. Losses 66,475. Winning percent 33.52%. So then if I come and change here and I rerun this, switched, yeah, I can tell that the new processor I have on my computer is great because we just went through that loop 100,000 times and it only pauses for like a teeny tiny moment. So now switch doors didn't, we need to have, okay, switch doors didn't switch doors. Let's go back. Switch doors didn't switch doors. Oh, got rid of my quotation marks. There we are. Switch doors. All right, I'm liking this layout a lot better. Switch doors played 100,000 games, won 66,688, lost 33,312, and my winning percent was 66.69%. So there we go. So in this quick little time here, we wrote an algorithm to prove that if we swap doors for our Monty Hall problem, you have a greater likelihood of winning the car. And that's what was so interesting about this, is that this was a huge deal back then. To give away a car back in the 70s, that was enormous. No show had ever done it, but they knew human nature. So people were only winning 33% of the time because nobody understood this statistical math problem. So they were winning twice as much as they were giving out cars. So they were getting ratings and not having to give away anything. As very few people were switching, the way that I read the news stories. So, all right. All right, Nico. I think it's just me and you right now. So, is there anything you want to talk about? Because probably, I don't know if we'll do it tomorrow. I don't know if I'll take off tomorrow or not. Let's see. Okay, good. I do have that. I do have that covered. So I think I like this layout. We could technically run both of these. 100,000 games. And then we run this twice. So we run each time through. We do a switch and we don't switch. I don't know if I want to do that or not. All right. Sorry. Let me switch over. All right, Nico. Anything you want to look at? Anything you want to talk about? Any design issues? Did you ever get the your global problem solved? Oh, did you see how I did that global thing? Because I'm trying to think. I have an example somewhere where I was passing. I wonder if it was my original design of this algorithm was that I was passing this back and forth. But there's also non-local, if I remember. Help. Non-local. Let's see. Here we are. All right, non-local. Non-local is a statement causes the list identifiers to refer to previous bound variables and their nearest enclosing scope, including globals. This is important because the default behavior for bindings is search for the local namespace first. So here's PEP 3104, access to name and outer scope, non-local statements, global namespaces. Let's look at namespaces. I don't remember looking up name. I don't know. No document. Now it just said, that's frustrating. It just said related help topics. Oh, I wonder if it's because is it case sensitive? It is case sensitive. Well, that is very interesting. Assignment, deletion, dynamic features. Okay, see, if you go into help and you look at this, you can go down a complete rabbit hole. Whoa. All right. We got namespaces here. Names refer to objects, which we knew that. Names are introduced by name binding operations. Okay. Each assignment block, resolution of names. Okay, scope. We understand scope. Exclude. So global, built-ins, enclosed. I gotta cheat and look up scope. Python scope. Python's LEGB. LEGB. Sorry. Local enclosing global built-ins. So local and then enclosed, then global, and then built-ins. That is the order of processing and where Python will look for a variable. It will look first for the local, then enclosed anywhere, and then global outside of this. Is it outside here? And then if it's not outside here, is it a built-in? Does Python already recognize it as something? That is how in the world the scope works. All right, so let's back out of here. All right, because I'm on the fence about going through and doing the chicken nugget problem again, because I have not built that in a long time. because we did prime, we did the nth prime. So I'm trying to think of all of the MIT problems that I did. I remember when I figured out, because I've redone the chicken nugget, I think once or twice, and that was pretty. I cleaned it up a lot because I was using a lot of breaks, and it was pretty bad. But I think I cleaned it up quite a bit, because I think I showed you my first is prime function, and that thing was I over-engineered that quite a bit. So let's see. All right, Nico. Anything pressing that you want to talk about before I drop? Because I'm at an hour and 20 minutes, and then I can do a couple things before I need to go head to jiu-jitsu. So I want to do that today and keep moving. I've got to do some housework. I got to fix a shower, and I gotta mow. I gotta fix a mower and then mow. So that's what my day is. I think you're on the other side of the globe, and so if you don't have anything, we're probably just gonna wrap it up here. But I give you a little look at it before we do go. Do you know the chicken nugget example? So I'll give you a little sneak peek. So the things about this is, I believe it's 6, 9, and 20. And I would not have even ever thought about this. Oh, very cool. Okay. Well, if you're working on that, I'll probably leave you be. But what I love is, because I wrote a very open-ended, and it was very flawed. My first one, it was very flawed. But what the concept is, how can you get a combination of these numbers to get them to add up to, let's say, 53? And that was crazy to me. That 6 plus 9 plus so what? 6 plus 9 plus 6 plus 20. And oh, okay, here we go. So if I were to add one more 6, I get 47. So then how in the world? So it was, how can I get, because I think the lowest number we could do was, I don't think it was 41. But I can't quite remember the lowest number that you could do. But once you got that low number, you could do any number after that. So what the principle was the original ask of the question was write a function, write an algorithm to find all of the combinations to get from 50 to 101, because it was really driving the point home. What are the combinations to get? It may have even been like 51. I need to go back and look at the original. 51 chicken nuggets and 101. And you can only use these three numbers. It blew me away. But I was able to go through and figure it out. All right. OBS is giving... No, not OBS. Actually, YouTube is giving me a warning that the stream quality is very low. But OBS is showing it's still green. I'm at like 64K bits per second. So I have no idea why and it's, yeah, I'm losing like 10% of it because yeah, chicken nuggets. YouTube is showing 3150 and OBS is showing 46. So I'm losing a quarter of my bit rate somewhere. Don't know if it's straight up on the upload on my side of my computer or my network. I got a wireless network going out into the world. All right. All right, Nico, if you're working on your website, I'm going to go ahead and probably wrap up for the day. Thank you, everybody, for joining us today, as always. I hope you all got something out of this, because this is a great step of moving from human brain to Python brain, and just drawing this all out and taking your time and going step by step and making sure you are following all your Python rules, because again, I wrote a lot of this all at one time and did not step all the way through, because I had the main big fail was I tried to pass in a number instead of a container, so I needed to change that, and I had this on the outside of this for loop, so I was not making a different decision every time this was happening. So actually, let's clean this up a little bit. No, I think I need that, because again, if I were to move this again, I would still have a problem. But I don't like that this is here. I don't like, but I need this to be called and I need this to be run every single time through. But I feel like this is ugly. But it is what it is. All right, it works. So it works. All right, Nico. Thanks for hanging in there with me today. We got almost an hour and a half in. I think we covered a lot. Handled some things here. Showed how to pull some variables out of a function, and with a new keyword that I don't think we've used yet, and used a round function that I don't think we've shown how to do that. So there we go. Let's run this one more time. That's 100,000. Let's see how long this takes to run 1,000,000. So another factor of 10. Let's see. All right, Nico. I will see you next time. All right. There we go. It paused for a second, but that's 1,000,000. That's 1,000,000 times through. All right. Hit that for loop 1,000,000 times, and it took maybe second and a half, 2 seconds. That's so cool. All right, Nico. I will see you next time. Thank you as always. Bye.